everyone, this is Shantan Kumar, Department of Mathematics, Assistant Professor, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today topic is applications of the Cayley-Hamilton theorem. Under the applications of this Cayley-Hamilton theorem, to find the inverse and powers of a matrix. Here, before going to discuss this one, in the previous classes, we discussed the verification of the Cayley-Hamilton theorem, and also I said clearly what are the applications. Once again, I am going to discuss here the applications of the Cayley-Hamilton theorem problems. That means to find the inverse of a matrix and also to find the powers of the matrices. These are the mainly two applications of the matrices under the Cayley-Hamilton theorem. Here, first of all, the given matrix is whether it is a 2 by 2 or 3 by 3 matrices, how to find the inverse of a matrix. Here, first of all, according to the Cayley-Hamilton theorem or any matrices, first of all, we need to find out what is the characteristic equation of the given matrix. That means we know that there is a delta of A minus lambda is equal to 0. And again, according to the Cayley-Hamilton theorem, we need to replace lambda is equal to A. That means it is in terms of you obtain that A. And again, that at the time of that lambda is equal to A, sometimes which is required A square and sometimes it is required that A cube. First of all, we need to find out by using the given matrix and by you consider the unit matrix, we need to find out what is a square and also I. We need to verify that is a characteristic equation. That means before going to verification that or finding the applications, we need to verify what is a Cayley-Hamilton theorem, and after that when we are going to finding that inverse of the matrix, that equation, that means characteristic equation, that is star is multiplication with A inverse, then you obtain the equation is the inverse of the matrix. And in that sometimes we are required to find out that is A square and also I. Sometimes the given matrix is the 3 by 3, we need to find out that is A cube also. Here, for example, we are going to discuss that one problem. Then that is using the Cayley-Hamilton theorem, find the inverse of the matrix where the given matrix A is equal to 1, minus 1, 2, 3. Here, according to the Cayley-Hamilton theorem, once again we need to find out what is the characteristic equation. The characteristic equation is equal to the given matrix is a 2 by 2. The general standard equation is S1 A lambda square minus S1 lambda plus S2 is equal to 0. That equation is treated as 1. And where S1 is equal to the trace of the matrix. The trace of the matrix here, the values are 1 plus 3. Therefore, 1 plus 3 is equal to 4. And similarly, we need to find out what is the S2. That S2 is equal to the determinant of the given matrix. The data of the matrix is equal to clearly by solving this matrix, that is 3 plus 2 is equal to 5 is a value. And again, after getting this S1 and S2, that what we are treated as equation 1, when we are going to replace in this equation 1, the equation is reduced to like lambda square minus 4 lambda plus 5 is equal to 0. And now, by using the Cayley-Hamilton theorem, we need to verify that is A square minus 4A plus 5I is equal to 0. Therefore, here, after getting that verification of this theorem, you multiplication by the process of that multiplication of that is inverse of a matrix. This equation is multiplication on both sides, that is inverse of the matrix. Therefore, that inverse into A square minus 4A plus 5I is equal to, the right side is also A inverse into 0 is equal to, the equation is changed to clearly, that is equal to A into, that is minus 4 into I plus 5 into I into A inverse is equal to, that is also 5 into A inverse is equal to, clearly the value is 0. Next, coming to here, we need to find out that is A inverse only. Therefore, from this above equation, that is a 5A inverse is equal to 4I minus A is the value. And next here, we need to find out the A inverse is equal to 1 by 5 into 4I minus A is the value. Now here, that I is, we know that is unit matrix. That unit matrix is multiplication with 4. The matrix is changed to 4, 0, 0, 4. Minus A is a matrix is 1, minus 1, 2, 3. Therefore, here by subtraction, that is the difference of the two matrices and including that 1 by 5, the matrix is reduced to like A inverse into 1 by 5 of, that is a 3, 1 minus 2, that is a 1. Therefore, this is the procedure involved in the inverse of a matrix under the Cayley-Hamilton theorem. Second one, for example, verify the Cayley-Hamilton theorem and also find the inverse of the matrix, where the matrix is clearly given here, that is a 3 by 3. Therefore, the 3 by 3 values are, it is a 2, minus 1, 1, minus 1, 2, minus 1, 1, minus 1, 2. First of all, according to the procedure, we need to find out what is the characteristic equation. The characteristic equation, as we know that is a lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. And again here, that equation is considered 1. And again, we need to find out first of all what is the s1, that is a trace of the matrix. The trace is equal to here 2 plus 2 plus 2 is equal to, that is the value is 6. Therefore, similarly, we need to find out what is the S2. That S2 is equal to the sum of the minors of the diagonal elements. Here, the sum of the minors of the principal diagonal elements are clearly 1 by 1. That is a first element is a 2. That is a corresponding the minor is a 2 minus 1 minus 1 2. The second minor of the element is a 2 is equal to, that is a matrix is changed to like 2 1 1 2, and the third minor is also the given matrix is equal to the data of, that is 2 minus 1 minus 1 2, and when we are going to addition of these three matrices, that is minus, the value is equal to, that is clearly we obtain 3 plus 3 plus 3 is equal to, that is the value is 9. And similarly, we need to find out what is the value of S3. That S3 is equal to, that is the meaning of the determinant of the given matrix. Therefore, the data of 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2 is equal to, after that finding the determinant, the value is equal to, clearly we obtain the value is a 4 only. And similarly, by using this S1, S2, S3 in the equation by replacement of, that is 1 is equal to, that is S lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0 is changed to, clearly that is lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. This equation is, for example, we treated as the second one. Now, we want to prove that this is the verification of the Cayley-Hamilton theorem first of all. Therefore, according to that verification of the Cayley-Hamilton theorem, now we are going to replace the lambda is equal to a. Therefore, the equation is reduced to, like clearly, a cube minus 6a square plus 9a minus 4a is equal to 0. And now, in this equation, now first of all, we need to find out what is the a cube, what is the a square, what is the a, what is the meaning of I. First of all, when we are going to find out in this matrix a square, that a square is equal to a into a, as we know that a is the given matrix, that is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2, and similarly one more matrix which is multiplied, therefore is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Then according to the product of these two matrices is equal to, we obtain clearly, that is a 6 minus 5 5 minus 5 6 minus 5 5 minus 5, that is a 6 value. And similarly, we need to find out what is a cube. Therefore, a cube is equal to, clearly that is a square into a. As we completed just now, it is a square is equal to this value you have to replace, that is 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6, and into the given matrix is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. The product of these two matrices, clearly we obtain, that is equal to, values are with respect like 22 minus 21 21 minus 21 22 minus 21 21 minus 21 22. Now, by using this a cube and also a square and the given matrix, that is a and including the unit matrix, one by one, it is the first we need to replace a cube minus that a square is multiplied with a 6. The matrix is also changed to like 36 minus 30 30 minus 30 36 minus 30 30 minus 30 36, and similarly plus 9 into the given matrix is multiplication like a. The values is also changed to like 18 minus 9 9 minus 9 18 minus 9 9 minus 9 18 minus 4 into multiplication with the unit matrix, that is equal to 100 0 1 0 0 0 1 is changed to clearly minus 4 into that is a 4 0 0 0 4 0 0 0 4. By solving these are the four matrices including the addition and also subtraction with corresponding that each and every element, the matrix is finally changed to clearly we obtain in the form of that is a 3 by 3 of order 3, that is a 0 matrix. Therefore, here it is a 0 is a meaning. Therefore, the meaning of here a cube minus 6a square plus 9a minus 4a is equal to 0. Thus, the matrix is satisfied clearly, that is a Cayley-Hamilton theorem. But in this problem, we are going to discussing not only the Cayley-Hamilton theorem verification. With the help of this Cayley-Hamilton theorem, now we need to find out the inverse of the matrix. As we discussed that first problem is based upon the 2 by 2 matrix, but this the problem is a 3 by 3 matrix. And here also, whatever we treated as the equation 2, that is a cube minus 6a square plus 9a minus 4a is equal to 0. This equation is multiplication according to the procedure of the Cayley-Hamilton theorem, that is inverse multiplied on both sides. Therefore, by applying the inverse on both sides and clearly one by one, that a inverse into that is a square, a inverse into a cube minus 6a square plus 9a minus 4a is changed to that a square minus 6a plus 9i minus 4 into a inverse is equal to 0. But we need to find out what is the inverse. But here, while we are observing in this equation that minus 4a square, we are going to consider the right side, that is 4a inverse is equal to the remaining matrix is a square minus 6a plus 9i. And again here, from that equation, once again, if we want to repair that a inverse, that a inverse is equal to 1 by 4 of that is a square minus 6a plus 9i. And in this equation, we know that already that a square is equal to, we need to replace that is 1 by 4 of that a square is equal to 6 minus 5 5 minus 5 6 minus 5 5 minus 5 6 minus 6 into a is nothing but it is 12 minus 6 12 6 minus 6 12 minus 6. Last row is 6 minus 6 12 plus 9 into, with the help of that I matrix, we obtain clearly that is 9 0 0 0 9 0 0 0 9. And one by one, when we are subtraction and including the addition of all these three matrices, finally we obtain clearly that is 1 by 4 into, according to that 1 by 1 each and every element that is equal to, including the addition and also the subtraction, the values are changed to like 6 minus 12 plus 9, minus 5 plus 6 plus 0, 5 minus 6 plus 0, and second row is also corresponding, that is a minus 5 plus 6 plus 0, 6 minus 12 minus 9, minus 5 plus 6 plus 0, and the third row is like 5 minus 6 plus 0, minus 5 plus 6 plus 0, 6 minus 12 plus 9 is by addition and including the subtraction, we obtain clearly that is 1 by 4 into 3 1 minus 1 1 3 1 minus 1 1 3. Therefore, this is the value of inverse of the matrix by using the Cayley-Hamilton theorem. And now we are going to discuss that one other problem by using the Cayley-Hamilton theorem to find the powers of the matrix. That is, here we need to find out what is the value of a power 4. And again, here when we are going to observing this matrices, first of all, we need to verify the Cayley-Hamilton theorem. Again, according to the Cayley-Hamilton theorem verification, we need to satisfy the characteristic equation. First, we need to find out what is the characteristic equation, that is delta of a minus lambda I is equal to, we obtain clearly that is a lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0, and corresponding we need to find out what is the value of s1, what is the value of s2, what is the value of s3. That s1 is equal to, we know that clearly there is a trace of the matrix. Here the trace is 1 plus 1 plus 1 is equal to, that is a diagonal elements, the value is 3 only. And similarly, we need to find out what is the s2, that s2 is nothing but the sum of the minus of the principal diagonal. Here the minus of the diagonal elements are 1 1 1. Therefore, we need to find out the three values independent, that is a minus of the matrices. That therefore s2 is equal to, that is first one is the value is the data of 1 1 3 1. The second date is also 1 2 2 1. The third date is also the minor is nothing but 1 1 3 1. The addition of these three, the minus of the given matrix is equal to, that is a minus of the principal diagonal elements is equal to, therefore the value is equal to clearly, that is equal to minus 2, minus 3, minus 2 is equal to, that is a minus 7. And similarly, we need to find out what is the S3, that S3 is equal to the determinant of the given matrix. According to, we know that the determinant of this matrix is equal to, clearly by solving we obtain that properly the value is equal to 11. Hence, by using this S1 and S2, S3, by replacement of in the equation, that is a characteristic equation, clearly we are going to change it to like, that is a lambda cube minus 3 lambda square minus 7 lambda minus 11 is equal to 0. Here this equation is treated as the second one. Then now we want to verify the second equation is satisfied the Cayley-Hamilton theorem. According to the Cayley-Hamilton theorem, we need to verify that is a cube minus 3a square minus 3a minus 11 is equal to 0. Then we need to find out what is the values are a square, a cube and also I. First we need to find out a square, that a square is equal to a into a. Therefore, already the given matrix is a. Therefore, by applying the given matrix into, once again the given matrix is equal to the product of these the two matrices 3 by 3, we obtain that clearly one other matrix is equal to, that is 8, 8, 7, 8, 7, 8, 13, 8, 8. And similarly, now we need to find out what is the a cube. That a cube is equal to, we know that a square into a. Therefore, that a square is equal to, just now completed, the value is equal to 885, 7878, 1388, and a is equal to the given matrix is a clearly 112, 311, 231. By multiplication of, that is nothing but the product of these two matrices, clearly that is a 42, 31, 29, 45, 39, 31, 53, 45, 42. By using this a square, a cube and the given matrix A and including the unit matrix according to, while we are going to replace in the given equation, therefore that is a cube is equal to this matrix minus 3 into the given matrix is replaced in the given matrix in the equation, that is equal to, that is 24, 24, 15, 24, 21, 24, 39, 24, 24 minus 7 into the given matrix is A is equal to that multiplication. After that simplification, you obtain clearly that is 7, 7, 14, 21, 7, 7, 14, 21, 7, and with the help of the unit matrix I, that is a multiplication with 11, the matrix is also changed to like, that is a 11, 0, 0, 0, 11, 0 and 0, 0, 11. And finally, by addition and including that subtraction, the matrix is changed to clearly, that is a 3 by 3 order, that is a unit 0 of the matrix. That is nothing but all the elements are, we are going to change it to reduce it to 0. Hence, it is 0 is nothing but the equation is satisfied the Cayley-Hamilton theorem. That is the meaning of the square matrix is satisfied, that is a characteristic equation. That is the meaning of the verification of the Cayley-Hamilton theorem is completed. Now, we need to find out what is the value of the a power 4. This is also one other property under the Cayley-Hamilton theorem. That is a second one application. First one is finding the inverse, and again second one is finding the powers of the matrix. Now we are going to discuss the second application, that is to find the powers of the matrix. And again, according to that, whatever we treated as a characteristic equation previously, that is a cube minus 3a square minus 7a minus 11 into y is equal to 0. While we are observing in this equation, the highest power is the a cube, but we need to find out that is a power 4. Due to that reason, we are going to multiplication with a on this total equation, that is a equation is changed to like a power 4 is equal to a into, that is a 3a square plus 7a plus 11 into y is equal to, that is a 3 into a cube plus 7 into a square plus 11 into a. And here we need to find out what is the a square and also a cube. And as we know that already completed the verification of the Cayley-Hamilton theorem, in that part there is a cube, we know that a square is also, we know that by using this a square and also a cube, therefore a power 4 is equal to, by using this a cube matrix, the matrix is reduced to like 126, 93, 87, 135, 117, 93, 159, 135, 126 plus 7 into, with the help of the matrix a square is equal to, you obtain clearly, there is a 56, 56, 35, 56, 49, 56, 91, 56, 56. Plus with the help of the given matrix A, the matrix is changed to like 11, 11 for 22, 33, 11, 11, 22, 33, 11. Including by using these three matrices addition, the matrix of the A power 4 is equal to clearly the correspondence values are one by one. Together addition of that corresponding one by one each and every element, that A power 4 is equal to we obtain, that is 193, 160, 144, 224, 177, 160, 272, 224, 193 is a value. Therefore, this is a second application by using the Cayley-Hamilton theorem under that to find the powers of the matrices. Finally, we concluded just now today in this class, that is by using the Cayley-Hamilton theorem, the majorly two applications are there. One is to find the inverse of the matrix, to find the powers of the matrix. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.